Okay, so right now let's look at convective mass transfer, right? Here we're talking about transfer of material between boundary, right? Boundary surfaces and moving of fluid, right? So between we have moving fluids, we are talking about bulk motion in general, right? So right here, you see that in heat transfer, we have what we call the heat transfer coefficient, right? Which is the H, right? So we have it in such a way that the flux, right? So over here, the flux will be equal to this one. We also have it equation when you're talking about in terms of mass transfer. We have the mass transfer coefficient, which is the Kc, right? Which is given by the flux being equal to the Kc. So this one over here is the concentration at what the boundary, and this was the fluid medium concentration, right? And the Kc over there is the one that we want to actually have to calculate for. Right, so for momentum diffusivity, where we have the viscosity divided by density, right, we call the kinematic what viscosity, right? And we have what we call the thermal diffusivity, which is the K, right? Thermal conductivity divided by rho Cp. Then you have the mass diffusivity, right? In terms of mass transfer, right? So over here, we'll be looking at some dimensionless quantities that you should be taking note of. So one thing is we call the Prandtl number, right? Which is the kinematic viscosity whereby thermal diffusivity, right? Which is also given by this one because of the mu, right? Which can also be given by this one. And the second one is what we call the Schmidt number, right? Which is the viscosity kinematic divided by the AB, or the dynamic viscosity over rho, because you know that the kinematic is given by the dynamic by rho, right? So you can also have the Schmidt number. The next one is what we call the Lewis number, right? Then you have what we call the Sherwood number, which that one we want to consider mass transfer, right? Let's see the Sherwood number. So the Sherwood number we're talking about is given by the K, right? The mass transfer coefficient times the length, that's times the length or times the diameter. We're talking about a circular thing divided by the AB. So that gives us the Sherwood number, right? Which in terms of when we're explaining it, it gives us what this explanation, right? So that's the Sherwood number, right? So the Sherwood number gives us that one. And the Sherwood number, you can say the Sherwood number depends on what? The Reynolds number and the Schmidt number. So when given a relationship for the Sherwood number, you want to actually calculate for maybe a Kc or any other thing, we need to get the Reynolds number and the Schmidt number. Right, so I give you the Schmidt number to be at this one divided by the AB. I know the Nusselt's number also depends on the Reynolds number and what's the Prandtl number. That's for heat transfer. I think it's here. Well, yeah, that's for heat transfer. So over here, if I see the fixed law 2 over here, so you can see it's similar to the Fourier's law of conduction, right? Heat conduction, right? And the Newton's law of what? Viscosity, right? They have similar thing. They have a driving force. So you can see there's a concentration driving force, right? That's for mass transfer. And this one, the temperature difference, right? And over here, you can see the driving force too over here. Yeah. And so that's what you have. So there are relationships, right, that we can use to actually evaluate it in terms of when you have a question, right? So this question, like this over here, they gave it to us and they told us that the for we should calculate the mass transfer coefficient, that's Kc, but they gave us the heat transfer formula, I mean relationship. So you know that Nusselt's number is equivalent to Sherwood number in mass transfer, right? So a Sherwood number, then 0.664. The next one is still Reynolds number to the power half. Then the Prandtl number becomes what? Schmidt's number. Right. So you just calculate Reynolds number, Schmidt's number, then we put it inside this equation. We get the Sherwood. The value that we get, we equate to the KCl over what? The DAB. Right. Then we can actually get what? The KC. Right. And that's basically it. So you see over here, we put all our parameters inside. We calculated for our KC. They told us to get the rate of loss, right? Which is the flux, right? So the K times the CI minus the C as infinity. So the concentration as infinity becomes zero. and the concentration at the interface, right, was 2 times 10 to the power minus 5. So you get that one, right? So that's the rate of loss of naftalene. And if you want it per unit what? Per meter width, right? Per width, right? You just multiply by what? The width, right? Which is 0.2. Then we get this, right? So you can have the relationship. So as you can see over here, we have the Sherwood for this for a flat plate, right? So this for when we have a laminar situation, you have a template situation. So a lot of relationships can exist. So when given that relationship concerning that particular question, you can just use that one to evaluate them. Right. Then you can also have this for a sphere. You can have this one, right? And here we have what we call the Peclet number, which is the Reynolds number times what the Schmidt number gives us the Peclet number. So we have a lot of relationships, right? Based on this one that we can use to solve that question, right? So let's look at an example of where to use this one to solve a question, right? So let's look at this example, right? So let's look at this example. Next example. So we have example um yeah. So let's look at the example 8, right? So they said that, so example 8. And then calculate the convective mass transfer coefficient, right? In a weighted wall column for the transfer of benzene into carbon dioxide at 0 degrees Celsius. The gas velocity of the column is 1.25 meter per second. The diameter was given, and assume the benzene concentration in carbon dioxide is very low. So based on this situation, right, they give us a certain equation for the Sherwood number, which is 0.023, Reynolds number to the power 0.33, then Schmidt to the power 0.44. Right. So based on this question, that's the model that fits this question, right? And they give us so the density of carbon dioxide, right, at those conditions is 1.966 kilogram per watt meter cube. Then the viscosity is 1.35 times 10 to the power minus 3 Pascal seconds, right? I mean, based on these conditions, right? That's what we have. So right now, our aim is to calculate for the K. Right, so for us to get the K, I need to get my Reynolds number first and my Schmidt number. You get this, but if I have to calculate my kinematic viscosity, which is this divided by this one, right? So I have 1.35 times 10 to the power minus 3 divided by 1.966. So I get 6.87 times 10 to the power minus 6 meters squared per second, right? So that's the kinematic viscosity. So now I can get my Schmidt's number, which is this one divided by the AB, right? And based on this one too, so I'll be getting 6.87 times 10 to the power minus 6. And my DAB, based on these conditions, was this one, 5.28 times 10 to the power minus 6, which gives me a Smith number of what, 1.3. And I get my Reynolds number, which is rho VD divided by mu. So the rho, right, the rho is 1.9, right, but the rho is that one. Then I know that the um rho divided by this one, right, the inverse, right, gives me, so I'm getting rho um, by the inverse, right, so I'm getting rho d divided by the kinematic viscosity, right? So I'll be getting 1.25, right, 1.25 multiply, that's the velocity, multiply by the diameter is 1.6, sorry, so right here becomes VD. Right, VD divided by this one. So divided by 6.37, so 87. times 10 to the power minus 6. So this gives me a Reynolds number of 29112. Right, so that's the so now I can have my Sherwood number to be 0.023, Reynolds number of 29112 to the power 0.33, then 1.3 to the power 0.44. Right, so now the Sherwood number becomes 130.9. So using this relationship, I have Kc times D divided by DAB. And that's the Sherwood formula. So I have 130.9. Right, so I want to find Kc. So Kc will be 130.9 multiplied by the AB, which is 5.2 times 10 to the power minus 6, divided by the diameter, which is 0.16. Now this gives me a Kc of 4.3 times 10 to the power minus 3. So this is it. Nice. So that's my Kc. Nice. You see, this is a very simple way to actually solve for um questions like this, right? Actually solve for questions like this. Yes, yes, yes. So that's it for question 8. Right. So this is question 8 where they ask us to calculate for the Kc. So right now, let's look at some concepts before we dive into question 6. Right? Let's look at some concepts before we dive into question 6. So some concepts on interfacial mass transfer. And so as you can see over here, you can see that we have a bulk liquid. Right, so here we have a liquid film over here, right? Then we have a gas. So this is the concentration at the liquid interface, right? And this is the concentration at a certain point B. Right? So this is assumed to be that this one, right? And you have a pressure 2 over here, right? Also in the gas phase. So in the liquid phase, you have a concentration. Gas phase, you have what? You have a pressure, right? So you have a pressure over there. Right, so you have what you call the film theory where we use the fixed law to actually get the Kc, right? So the Kc, mass transfer coefficient, becomes the AB divided by what? The thickness, right? Based on this relationship, right? Based on this relationship, so we can have that one. If we have a bulk flow effect too, it becomes this one, right? So you know that the Kc is directly proportional to the AB from this formula, right? So you can have two resistance theory, right? Where over here you can see that we have a gas phase and this is the film. And you have a liquid film and a liquid phase, right? So over here, this is the interface. So you have the pressure of the gas at the interface. Then you have the concentration also of the liquid at the interface, right? Then this is the concentration in the liquid phase, and this is the pressure in the gas phase. So the transport is occurring in this sort of direction. So you see that we write, so in the liquid phase, you see that we are using the concentrations or using the gas phase, right? So it becomes the concentration at the interface minus the concentration in the bulk, right, in the liquid phase. And this one becomes the pressure in the gas phase minus the pressure at the interface. So you take note so that you don't switch them, right? Right, so you don't switch them up. Right, so yeah. So over here we have some relationships that we can deduce, right? So based on some assumptions, whether we have the Henry's law, right? So whether we have the Henry's law or so the Henry's law, where we have let's say YAP becomes XA at HA, which is the Henry's constant, right? So this is the Henry's law, right? Or they can also tell you that it obeys what you call the Raoult's law, right? So you can also obey the Raoult's law. With the Raoult's law to where we have YAP becomes XA PA sat, right? That's the saturation pressure. This is when we have an ideal gas situation. When we don't have an ideal gas situation, they have to introduce the activity watt coefficient over here. Hmm. So in this case, we can actually use the what we call the Antoine equation to calculate for the saturation pressure, which is this one. Right, so AI minus BI divided by CI plus T. So we use this one to calculate for the saturation pressure. So the thing can obey the Henry's law, or you can obey the Raoult's law. So based on any of those two, you can get the equilibrium, right? So here is it that based on this equation, we got a certain equation. So this is a relationship that exists between the coefficients. So this is the coefficient, right, in the liquid phase, right? And this one over here, right, is the small ones, right? So this is the overall resistance, right? And this one is just due to the liquid phase, and this one is due to what? The gas phase because of the Kp. You can also have another relationship, right? This is just when the Kp is the subject, right? And you can have another one, right? So when you have Ky and all those things, right? Yeah. So we have all these relationships that exist, right? So you're talking about interfacial. Um, you're talking about interfacial. This is the Raoult's law, right? So based on this one too, right? We can get the y equals something. Then we can use the Antoine equation to actually evaluate. So these constants are, you can get them in Harry's handbook, right? And all those chemical engineering books that you can get them from. Right? So let's see the example number 6, right? Question number 6. So so the so the question number 6, right? The question 6, we have they said that in a dilute concentration region, data for data for SO2 distributed between air and water, right? So we have PA to be 25 at XE, right? So that's PA, right? PA is 25 XE, right? And you know that the mole fraction is the partial pressure of E divided by the total pressure, right? So if I have this one, PA is 25 XE from the equation given, and the total pressure given in the question was to be, they gave us and the total pressure is 10 atm. Right, so here I'll get 2.5 watts XE. And so this gives me the relationship, right? Right. So you told me that it follows what this equation. So this gives me the relationship between YA and what XE. Right. So the question told us to calculate for find KX. Right. After finding KX, we should determine the interfacial compositions XAI and YAI. Then we should also calculate for the molar flux, which is NE. Right. So for us to actually do that, right? So for the A, yeah, I need to get this equation. So over here, this one becomes the overall divided by, so I have M ky plus 1 over small kx, right? So over here, you can see that I can actually find the big kx using this expression, and the M is what, the 0. The M is the 2.5 over here. So it's 2.5. They gave me ky due to the just the gas phase, right? They gave me to be 8. Then this one becomes 10. Right, so when I evaluate the kx, right, it gives me 6.67, right, 6.67 kilomole per meter squared, right, so kilogram mole is in kilomole, right. So this is what I have for E, right. That's the, it's very easy to get the E, yeah, based on this equation. You can also have another equation just for ky, so 1 over big ky becomes 1 divided by ky plus m divided by kx. So based on all these equations, you can get whatever you want to calculate for. So if I ask you to calculate for ky, then you sort out to this equation. Right? So the next thing is for us to also calculate for. You told us to calculate for the interfacial compositions, right? So for us to calculate for the interfacial compositions, right, we have to find the slope, right? And the slope is given by minus k, right, minus kx divided by ky, I mean the small ones, right, which is ya minus at the interface, right, divided by xe minus XA at the interface. Right. So this one is minus, so it's 10 over 8, right? Very simple. So you find the slope, which is minus 1.25. Right. So after getting this slope, we set up an equation, right? So where the equation becomes YA will be equal to minus 1.25 XA, right? Because that's the slope, plus 0.01. Why is it plus 0.01? Because they told us in the question that the liquid concentration at one point in the column are, so YA was 0.01 and XA was 0.00, right? But in a case that we don't have the x component to be 0, this is how you model it. So the YA, right, will become minus 1.25. Then here becomes XA minus what? XA star, right? Then plus what? YA. So in that case, this is how you model it, right? When the when that XA is not 0, but when it's 0, since it's 0, this is how we model it, right? So based on that equation, right? So let's say this so based on this equation, let's say this one is equation 2, and this equation we have YA equal 2.5 XA, which is equation 1. We solve the two equations simultaneously to get the interfacial concentrations, right? If we solve it simultaneously, XAI becomes 0.00267, then the YAI becomes 0.0067, right? So right now you can actually calculate for me. So this is an easier approach to calculate for all these things based on this question here over here. So you can get the interfacial compositions, right? XAI and YAI. So right now you have them, and based on that one. And the last one told us to also calculate for the molar flux, right? Which is NE. Okay. So the molar flux NE. And so right now the molar flux NE becomes so you can write it. So this I'm using kx. So if I use kx, here means that here will be XA at the interface minus XA. Or I can also use the ky, where that one I have to use YA minus YA at the interface, right? So you can use any of them, right? So I'm using the first one, which is 8. Then you have 0.00267 minus was 0 because XA was 0, right? From the point that was given over there. So this one gives me 0.0267, right? I have kilomole per meter squared, right? Right. If I try the other one too, so the ky was 10, so 10, then YA was 0.01, right, from the question, right? So YA was 0.01, then minus the 0.0067, right? So if I compute, I have 10 multiplied by 0.01 minus 0.0067, and that actually gives me 0.033 kilomole per meter squared. So which this one is approximately 0.103. So yeah. So you either use this one or use that one to actually get. So your ability to be able to remember all these relationship, these equations that relate with these things that has been given over here will be able to go a long way to help you to actually calculate for your kx, your ky. Right. They can actually, so this one over here is what you call the resistance. So 1 over the constant, 1 over the key is what you call the resistance, right? So this is the overall resistance. This is the resistance due to the gas phase, the resistance due to the liquid phase, right? So you can just be you can be asked to find the resistance, right? The resistance due to the gas phase, the resistance due to the liquid phase, or the overall resistance. So yeah, the 1 over that thing is what you call the resistance, right? Yes. Now let's look at the question over here, which is the carbon dioxide question. Right. So the question 7 over here, in the carbon dioxide is absorbed in water at all these things. They told us that for the system to be assumed For this system, it may be assumed that 98% of the resistance to mass transfer occurs in the liquid film, and they give us the overall coefficient kg in the gas phase to be 0.93, right? So that for the equilibrium curve, right, using Henry's law can be expressed in terms of 1.42 times 10 to the power 3 what xe, right? So based on this one too, we can actually get as I always say, we can get they give us the total pressure to be 1 atm, right? So 1 atm, so we can have YA to be equal to PA over PI. Here 1.42 times 1 power 3 xe divided by what? 1. So it becomes 1.42 times 10 to the power 3 xe. Right, so that's the Y. So you have that equation, right? And they told us to yeah. So that question so for this question they told us to get the coefficient, right? They told us to get the question over here, right? The actual question is to find the KL, right? In the liquid phase, you want the concentration in the liquid phase, right? And there were some other questions too. So that one we use 1 over the big kg, right, is equal to 1 over the small kg plus m divided by KL, right? In the liquid phase. This is a small, not big one, right? So based on this one, they said that 98% of the resistance to mass transfer is in the liquid phase, right? Or the liquid film. So which becomes m divided by the small KL, right? So that's the liquid film, right? It's 0.98%, right? So divided by what? The big kg, right? So this right now, right? So that if 98% is over here, that means that for the gas phase will be what? Just 2%, which is 0.02 of what? The total resistance, right? Which is this one, right? So the small kg over here will give us 0.02 divided by 0.95, which is given in the question. I have 47.5. I have mole, right? So I have kilomole per meter squared ATM, right? I have this one now, right? Then I can actually also calculate for my KL, right? So KL from using that formula it becomes the M small kg, um, the M big kg, I mean big kg. So using the equation, finding KL is divided by 0.98. So the M from the question is 1.42 times 10 to the power 3 times the kg, which is 0.95, divided by 0.98. Yeah, this one gives me 1376. We have kilomole per meter squared. Right. So this is due to the liquid phase and this is due to the gas phase, right? So that's what the question told us. For your ability to even remember all these relationship that exists between them and your ability to convert the resistances. So they said that 98% of the resistance to mass transfer occurs the liquid phase. So the liquid phase resistance, right, is 98% of what the total resistance, which is 1 over big kg. So that means that due to the gas phase, right, it will be just 2%, 0.02 of what the total resistance. So that can help us to get the kg and get the kl, right? Very easy to do. And so the interfacial mass transfer, they can be asked you to find the interfacial compositions, that's xai and yai, where there can be. So this equation I was given in terms of Henry's equation, there will be a point that maybe you get maybe Raoult's law, right? They can tell you that it follows Raoult's law, but they won't give you the actual thing. So you have to write down equation. You put in your terms, right? Your pressure, right? So all those things, so that you can simplify to get the equilibrium. Why you got something like C. Then based on that, can be able to solve for everything that you need to remember all these formulas and finding the flux NE, finding KC, and all those things, right?